How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at phase changes. So our objectives will be to describe what is happening on an atomic level during various phase changes. So let's talk about solids. Quick review. Solids, we know molecules are locked into position. They can vibrate in place, but they can't flow past each other. They got this definite shape, a definite volume, and they're incompressible, right? So solids kind of look like that. They're wiggling around. The intermolecular attractive forces are high because they're really close together. So the closer you get to things, the more attracted they are going to be to each other. Think about magnets. Far apart, barely any attraction. Get them close, they're sticking together real good. Liquids, molecules can flow past each other, but are still very close to each other. Take the shape of the container, they got a definite volume, they're incompressible, and this attractive force strength would be considered like medium. Some molecules will evaporate and cause a vapor pressure, and we'll talk about that more in another video. But then we got gases. Molecules can flow past each other, and they're very spaced out. So they take the shape of their container, they take the volume of the container, they're compressible, and the attractive forces between those gas molecules is really low. So energy and phase changes. Let's talk about energy. Common experiences, maybe something you could relate to. If you ever stepped out of the pool or a shower that has had the door open, you feel cool. And why is that? Because the water on your skin evaporates. And in order to evaporate, it needs to absorb energy and it takes it away from you and you feel cool, right? We know that ice in your beverage keeps it cold. How is that possible? Because as the ice melts, it absorbs heat from your drink, keeping it cold. And then if you've ever made tea or something, you may have burned yourself on some steam. How is that possible? Well, what happens is the hot vapor condenses into a liquid on your skin, and that process releases a whole lot of energy, absorbed into your skin, burns you, and you're having a bad time. All right, so phase changes. We got solid, liquid, gas, right? Let's talk about the endothermic processes where it needs to absorb energy in order for that to happen. So we know going from solid to liquid, you probably know that's called melting. You know, liquid to gas, it's called vaporization. And then we also have a phase change from solid straight to gas that we call sublimation. All right, so if we went in the opposite direction, we got exothermic processes where the substance needs to lose energy, needs to give off this extra energy. So if we went in the opposite direction, from gas to liquid, we got condensation. Liquid to solid, we have freezing. And then from gas straight to solid, we have deposition. All right, so those are the exothermic processes. So let's talk a little bit more about energy. Solid liquid equilibrium. If we go from solid to a liquid, we call that melting. It needs to absorb energy, so that process is endothermic. You want to melt some ice, you got to give it some energy. Go in the opposite direction, freezing. If you want to freeze some water, you got to get rid of some energy that that water has, so it needs to lose that energy. That's exothermic. This process and the energy associated with it, we call the heat of fusion, or delta H fuse. Right, so if you're going between solid and liquid, this value you're going to use. For your water, it's 6.01 kilojoules per mole, or 3.34 joules per gram. So if you had a sample problem, like how many joules are required to melt 2 grams of water at its melting point, you would go, hey, 334 joules per gram times 2 grams, grams cancel out, and you'd end up with 668 joules for melting that much water. Right, between liquid and gas. Liquid to gas is vaporization. It needs to absorb energy, so it's endothermic. You want to boil off some water, you got to heat it up. That water needs to absorb the heat, it's endothermic. The opposite direction, exothermic, condensation. That water vapor needs to lose energy, which is an exothermic process. So for that, we use the heat of vaporization for both directions. You may be thinking, hey, if it's going from gas to liquid, why do we call it vaporization? We do. All right, it's the same thing, just opposite directions. So for the water, it's 40.7 kilojoules per mole, or 2,260 joules per gram. So example problem, hey, how many joules does it take to vaporize 3 grams of water at its boiling point? Well, you go, all right, well, I got 3 grams times 2,260 joules per gram, and you end up with, like, what is it, 6,780 joules. So there you go. All right, between solid and gas, from solid to gas, we call sublimation. It needs to absorb energy, so that's endothermic. Opposite direction, exothermic. Deposition. Heat of sublimation, delta H sub, is the energy for that process. For water, it's roughly 47 kilojoules per mole. And hey, wouldn't you know it, that the heat of sublimation is kind of exactly the same thing as the heat of fusion plus the heat of vaporization. So if you're trying to go from here to there, it's the same thing as doing these 2 steps added together, right? And if you take a look at the math, heat of fusion is roughly 6.01 kilojoules per mole. Heat of vaporization is 40.7. When you add those together, you get roughly 47 kilojoules per mole. So it's those two things added together. All right, fusion versus vaporization. Fusion tends to take less energy than vaporization. So if you're trying to melt something, that's going to take less energy than vaporizing it. And if we take a look at the phase diagrams, you can see the difference between a solid to a liquid. Well, hey, they're still really close together in the liquid phase. They're just able to move about. And that takes, for water, 334 joules per gram. But, that's only because we need to just weaken the attraction of the particles so they can flow, but they're still really close together. But if we look at the liquid to gas thing, there's a big difference there. We need to overcome the attraction entirely to separate those molecules apart. And that's going to take a lot more energy. And you can see that in the value. It's almost 10 times more. It's probably all right, I lied. Maybe it's 7 times more. So critical temperature and pressure. We know gases can flow past each other and are very far apart from each other. We know that liquids can also flow past each other, but are still very close. So the only real difference is how close or far apart they are, right? That's the big difference. So that means if you increase the pressure on a gas, you can force those gas molecules to become close together and turn it into a liquid. So if we were to push down on the top here and it were to come down and compress all of those gas particles, we can get them so close that it's like a liquid. So we know in the gas phase, the kinetic energy of those gas particles is significantly greater than the attractive forces between them. And that's why they stay far apart. They got so much energy that even when they bump into each other, the attraction can't hold them there. But we also know that attractive force increases with proximity. The closer those things get to each other, the stronger the attractive force becomes. So if we force them to get closer together by increasing the pressure, then we flip that. Now the attractive force strength is stronger because they're stuck close together, stronger than the kinetic energy. That means that they can become a liquid phase. So this is if you ever had these LP, liquid propane gas tanks, that's pretty much what happens. We're pumping in all these gas particles and filling up this tank, and we keep increasing the pressure until some of it turns into a liquid at the bottom. So if you've ever sloshed it around, you can feel if there's propane in it or not. And what happens is when you open the valve, the pressure drops and the gas can come out. So as the pressure drops, more of the liquid vaporizes to replace what's coming out. And that's how liquid propane tanks work. Pretty cool, in my opinion. All right, so at a high enough temperature, no amount of pressure can cause a substance to liquefy. So at a certain temperature, the kinetic energy is always going to be greater than the attractive force, regardless how close you get them together. You can increase the pressure and force those particles to be closer together, but they're never going to condensate or condense into the liquid form. That temperature, the max temperature at which a liquid can still exist, is called the critical temperature. So I got a little phase diagram here. We'll learn more about those later, but it shows what phases are present. So, low temperature, low pressure, we end up with a solid, low temperature, higher pressure solid. We got liquids over here. We got gas right here. At a certain high enough temperature, boom, right here, that's the last or the highest temperature at which a liquid can exist. If we went any higher, it would have to be in the gas state. So the critical temperature is that temperature right there. Any higher, it's got to be a gas. Critical pressure is the pressure required at that temperature to turn it into a liquid. All right, so that's the critical pressure. So the stronger the attractive forces are, the higher the critical temperature will be. If they're really attracted to each other, you're going to need a much greater kinetic energy in order to overcome those attractions, which means if we had a weaker attractive force, that critical temperature would be lower and lower and lower, and be like, hey, because the attraction is so weak, maybe this is our critical temperature. That's the highest temperature it can be before it'll be a gas. All right, so we got this new phase we're going to talk about real quickly. So we know that, hey, we've always known solid, liquid, and gas, and that's it, right? No, things are, of course, always more complicated. So new phase, supercritical fluid. basically you cannot distinguish between gas and the liquid phase. It's kind of the same thing. So it'll expand to fill its container, which is very much like a gas, but the molecules are also very close together, which is liquid-like, but the attraction to each other is still almost non-existent. So that's very gas-like. And if you take a look on this particle phase diagram, it's this whole region up here. That's where the supercritical fluid state is. So this occurs when temperatures and pressures exceed the critical temperature and pressure. So up over in that area is where you find it. So basically what happens is, like, let's say we got this liquid and we got the gas above it. What happens is, hey, pressure keeps increasing, keeps increasing. We end up with this state of matter that is kind of solid, or kind of liquid and kind of gas. So summarize, can you describe what is happening on an atomic level during various phase changes? I hope so. Hope you found it helpful. See you in class. Okay, bye.